Okay, so these are the review slides for exam 4. So with that, Organic 1, exam 4, fall 2016. So with that, so um, these are going to be the free answer parts. We're going to talk a little bit about the multiple choice section because this exam is going to be on chapter 6 and what we covered the partial chapter 6, or excuse me, partial chapter 7. So with that, so the chapter 6, as it turns out, is going to be a lot of because there's a lot of trends as far as the acid base strength and how you work with pKa's and do you understand them. A lot of those are going to be free, the multiple choice stuff like that. But there are some things you need to look at as far as trends go, as far as like what makes a good acid, what strong acid, things like that. So we'll talk about that, stuff like that. But these are the these are the free answer part, right? So with that, so we're looking at, so one of the things would be circle and label the molecules acting as the acid and base. Okay, it's just the acid base, not the conjugate acid conjugate base, just the regular acid and base. Okay, so what you're going to do is you say, okay, you look at the molecule, look on this side versus this, going from here to here, right? It is losing this. This should say Bronsted. Okay, but in going from here to here, it's losing a hydrogen. Okay, so with that, and then here, right, this molecule is gaining a hydrogen going from here, from reactants to products, right? So this is going to be our acid. Okay, this is going to be the base. Okay, so with that, so the thing that loses the hydrogen, that's going to be the acid, just like HCl loses a hydrogen when it reacts with base. Okay. This is, the molecule that gains the hydrogen, going from products to reactant, or going from reactants to products, right? That is going to be the base. Not too bad. Okay. Now they are going to be drawing the reaction coordinate diagram. Okay. For us, in this case, we're going to do a spontaneous reaction. Okay. So this is the one where you're looking at plotting it. Okay. So with that, so we're going to say, okay, start here. Okay, so if it's a spontaneous reaction, right? So if this is reactants, okay, if it's spontaneous, that means it's going to be lower, somewhere above the baseline, but below the react. Right. So if here's the reactant, it's got to be below that. Okay, so products are here. They're going to be at lower energy. Okay, so we've labeled. So we have to label the reactants. We have to label the products. Okay. Then here, the transition state, that's just a hump, any sort of hump you want, okay? As long as it's, if it was non-spontaneous, it'd be up here, the products would have to be up here, right? It needs to be up above the products, right? The highest point of it, okay? So with that, so this is the transition state. This is the point of the reaction where you're at the highest energy, okay? Okay, so we got that. The delta G's. Okay, so the delta G's are always relative to where you started from. Okay, so the delta G to the products, okay, that's this delta G0. That relative to the products. Okay, so the delta G0. Okay, so we got that one. Now this one here, this is the activation energy. Okay, that's to the highest peak from where you started to the highest peak. Okay, so that is this here, delta dagger. Okay, so the delta G's are always relative to here. And there you go. So we got that. Okay, now you're going to have to draw a curved arrow mechanism. I'm going to show you 3 of them. You're only going to get 1 of those 3. Okay, so with that, but you need to know the molecule is going to look a little different, but the mechanism is still the same. Okay, so with that, so you're going to need to know these. Okay, but but you're only going to see 1 of them. But this way, I get to make you practice all 3. Okay, but I am going to show you. So this is what you're going to see here. You're going to see the products, or the reactants and the products. Okay, you're going to know how to go where you need to go. Okay, so you can go from here to here, right? So with that, we're losing a hydrogen. Where's the hydrogen going? It's going on to here. So what must be happening is one of these sets of lone pairs, right, for this acid base, is going to grab here and it's going to push those onto there. Okay, so that's the mechanism. You're going to see the stop reaction. I want to see how the mechanism goes. Okay, the other one you could potentially see is an SN2 reaction. Okay, so here's, you know, it's a substitution. I'm not going to put this in here, but you have to know, right, because we're substituting this OH for where that leaving group is, right? So this substitute swaps in. Okay, so in order to do that, right, this is our nucleophile, right? So we look to see, well, here's the polar covalent bond, right? There's partial positive, partial negative, right? So one of these sets of lone pairs must have come in to make a new bond here, and then that's to make sure there's not the fifth bond. You got to push that away. Okay, there, push that up to make that. There's our substitution reaction. Okay, now if you get this one, it's going to be a little bit more complicated, right? So it is, right? So you have to remember that this is essentially a methyl, right, with a set of lone pairs. Now here, what we've done is we've swapped this group for that whole leaving group here. Okay, so for here, that goes right here, right? Because this is a partial positive, partial negative, right? But the first thing that's going to happen is it's going to go up to there to get into this tetrahedral intermediate. Then it's going to collapse down and kick this away. These collapse down and then kick that away. I'd like to see, if you do this all in one step, that's fine. But if you push it here and just go here and then push that away, I'm going to take off a point. Okay, I want to see that that the electrons go up and then down and then push away. Okay, they come up and then they spring back down, push away your leaving group. Okay, so we know it's leaving group, right? Because it's like that. Okay, this is your leaving group here. So be careful with this one. If this is the one you end up getting. Okay. Now for the reactions, okay, this is a fairly I was hoping to get something a little bit better looking than this. Okay, so for acid base, right? So if you have an acid base reaction, right, you remove. So these are going to be what you need to do for the predict the product questions. Okay, so there's going to be 5 of these. They're not going to be these specific ones, but the reactions are going to be like these. But they're not. The molecules are going to be different. But you have to realize that the reactions are the same. Okay, so for an acid base, right? So again, what we're doing, right? So you know, for these, what's happening is, right? So we have a nucleophile, we have acidic hydrogen, right? It's going to rip this away. Now, how do you know? How do you know it's it's an acid base as opposed to an SN2? Well, one, this one's going to have an acidic hydrogen, but then also I would write SN2 if you wanted to. So if you're going to get the reactions that look like this, okay, it's going to look like that. You're going to have to predict what these products are. Okay, and so for here, if it's an SN2, right, we're going to have to swap in this nucleophile swaps in for that bromine. I'm not looking for, on the predicted products. I'm not looking for the mechanism. I'm just looking for the product that's formed, right? But it's always good to get partial credit if you can show me how you got there. Stuff like that. It's also helpful to know that you got to there and push that away. Okay. Now for nucleophilic substitutions, again, we're gonna you have a partial and negative, and again, another clue is I'm not going to put SN2 here. Okay, so again, you're going to have it attacking the positive thing, pushing it up, stuff like that. But you have to make, when it pushes this up, you have to take a quick look to see here and here, do I have a good leaving group? Okay, basically, if I only have carbon, so if I only have carbon groups hanging off here, or just hydrogens hanging off of here, what ends up happening is you end up getting stuck here. If there's anything else, you could probably go ahead and collapse it down and then kick whatever group is hanging away off. Okay? And stuff like that. Okay. Now for the Grignard, right, the lithium, and the Gilman, okay, what's happening is what is essentially going to be is a set of lone pairs and a negative charge here on that carbon, where, right, so here it's, here you get 2 bullets, here you only have 1. It's going to make a bond between wherever this metal bond is and your leaving group. Okay, so here's where the metal is going to go. It's going to make a new bond here, because that's where, right, partial positive, partial negative. It's going to make a new bond here. Here, same thing here, right? Bond. So make a new bond from here, and then where your leaving group is. Same thing here, right? So here's the group that's leaving, right? One of those comes in and displaces your leaving group to leave this. Okay, so with that, okay. Now the other reaction is the E2. Okay, and you'll see because I'll write E2 on here. You got a base, so right there, and so what you got to do is look on both sides, okay, and see if there's hydrogens here. Well, there's hydrogens here, right? So I could rip those away and make this product, or I can go on this side because the hydrogens have to be adjacent to it. Okay, there's hydrogens here and here, right? Well, then we could do it here, right? So we could do it either way. I want to see both products, okay? So with that, so on either side of that leaving group, okay? If there's 3 for whatever reason, then you could have a third or whatever. So with that, but you need to make sure that there's adjacent hydrogens that you can rip away. And the reason why you need to do hydrogens, right? Because you're making a carbon-carbon double bond, you have to have 2 carbons involved. Okay, so with that, and it has to be adjacent. If it's over here, right, it's too far away. You can't make a carbon-carbon bond from there to there. It's going to be too difficult. So with that, so it has to be adjacent to it. Okay, and just as a reminder, right, so with that, so your organometallics and your hydrides. Okay, so with that, so okay, so predict the products. Okay, so I said, oh, it's an SN2 reaction. We are going to substitute our nucleophile. We need to figure out our leaving group. Well, that's our leaving group here, and so it ends up being. All you got to do is substitute it like that, plus Br minus. If you forget the Br minus, you're fine. But for an SN2, you're just swapping in whatever your nucleophile is for this. And if there's groups hanging off of it, right? So if there's like an ethyl group hanging off of here, it would still end up swapping the whole thing. Okay, the whole nucleophile gets swapped in. Okay. Now for this one, I said it's an E2 reaction. Okay, so here is our leaving group. Okay, well, because otherwise there's nothing else there. Okay, and so that what you have to do is on either side, take a look. Well, on this side there's hydrogen, so it could go there. This side that there's hydrogen, so it could go there, right? So if we do it on the blue side, right, the double bond would be there. If we did it on the red side, it would be there. Okay, well, it ends up being plus H2O. Okay, this is on this blue side, right? Because we extracted right. This is where, that's where the leaving group originally was, right? So we're going to look on either side of it. Okay, see if there's hydrogens. Okay, now here, right? So with that, so that is essentially this. Okay, so this is going to attack there. It's going to kick up to make this intermediate. Okay, your tetrahedral intermediate. Okay, plus this CH2, CH3. Okay, now the question is, at this carbon here, is there a leaving group? Yep, there is. It's this here. So this is going to collapse and kick that away. So you're going to end up with this. CH2, CH3. Br minus. Okay. Now, trends. So these are some of the trends for the pH strength. Okay, so I forgot my periodic table, right? So, but if you're looking at carbon, nitrogen, oxygen, carbon, nitrogen, oxygen, fluorine, sulfur, phosphorus. Look at the common ones: chlorine, bromine, iodine. Okay, when the hydrogen is on the element, okay, what you're looking for is the closeness to iodine. Okay, the closer the atom is on the periodic table to iodine, the more acidic it is, right? So a SH bond is going to be more acidic than an OH bond. Hydrochloric acid is going to be more acidic than hydrofluoric acid. Okay, same thing here, right? So an OH bond is going to be more acidic than an NH bond. Okay, stuff like that. So there you go. The other thing you're doing, right? If the atom is sp hybridized, it's going to be stronger. If it's going to be the sp3, then if it's an sp3. Okay. Now, adjacent pi bonds help too, right? So if you have alcohol, right, is 16, right? It doesn't matter if it's a carbon-oxygen pi bond or a carbon-carbon pi bond. Having them adjacent to where this is helps, because we're going to have these resonance structures available. Okay, and again, all of these things are additive. Okay, or so we add up, right? So that you also have inductive effects. So the more electronegative, right? So here we're just talking about closeness to fluorine, right? So when you're just talking about electronegativity, you're talking about fluorine. Okay, so the closer it is to fluorine, the more electronegative it is. Okay, so the more electronegative you have, so the stronger the acid. Okay, the closer the electronegative atom is to the acid, where you're losing that proton, again, stronger, right? So you go from here to here, right? So you add in a chlorine, right? So next to it, so it's 4.8. You put something electronegative here, right? So 2.9, but the farther it gets away, 4.1, 4.5, to the point where it's almost back to where there aren't any. But if you had, say, an HBr here, this would say, so if you had here, so if you had HBr, right, it might be, the pKa, might be 3.5. Okay, if you had it, if you had a fluorine here, okay, this could be, the pKa could be like 2.2. I have no idea. I'm just making those up, but that's what the trend would be. Okay, and if you say you had, again, it's cumulative, right? So if you had 2 fluorines on here, right, the pKa might be, 0, something like that. Okay, again, it's cumulative. So as long as you keep those things, keep those in the back of the mind, so you can usually figure out which is the strongest acid. Okay. Good luck on the exam.